let's more questions about sampling? Yes.
I don't have a question, but just I hope for Stata people that on OECD website there are actually edu files that you can do the same things for Stata.
Yes, the OECD site, it's a good point. The OECD website has some code in Stata that does this and takes this into account.
So you can again?
The OECD website has some code in Stata that will implement this for some analysis. So it'll be for means and percentages and regression maybe, and logistic regression. So for a handful of analysis.
Yeah, I saw it.
Yeah.
We use that
I have a question, yeah. Are we doing lunch here or people are on their own?
Yeah, it's ready, so
What?
the lunch is ready, so it's up to you.
And we'll have lunch here?
Yeah.
Ah, okay, okay. So, do you want to take a break or you want me to continue talking? Huh? Break? Okay. Let's take a break. And so lunch is here then. Ah, okay. So, I'm a little behind. Not much, but we like catch up. So let's take a break then, and let's start at 1:30 in an hour.
Okay.
Yes. And then I'll talk about IRT. And then you will spend time reviewing the documents and stuff, and we'll do that.
Okay, thank you. So there will be some.
Já jsem nahrával long play, že to bude nahrávať 1.5 hodiny teraz.
Sampling. So, yes.
There are other European or international studies that know these features exactly. For example, they don't have replicate weights. So they just have a weight. For example, the European Social Survey has just.
Yeah, so the question is, are there other surveys that the European Commission does and other organizations do that may or may not have weights, and may or may not have replicate weights, and may or may not, and the answer is, I don't know about the surveys. I mean, I know there's surveys, and I would assume that people do a reasonable, honest effort to use proper methods to report the results and to include proper information in the database. In general, whenever you do a survey that it's like this, you need some sort of method to compute sampling variance that takes the sample size into account. The methods might vary, so they might put in there, some might do jackknifing, some might do bootstrapping, some might do Taylor linear. There's different methods, they're all estimates. So, often the things are ignored by the users. So, the fact that people don't use them, and you'll see there's more things. I mean, you see published papers that ignore the things, and they get by because people don't know how to do the right things. So, I'm not saying they're bad, I just don't know. But all I'm saying is that whenever you do surveys like this, you need to take the design into account, and that is sampling weights, and that's using some sort of method that's different from that to take into account to compute your uncertainty about your estimate. Okay, so let's get into something more magical, and I do mean more magical for some people. But so we have a design, and I think I hinted at that earlier, where some people take some items, nobody takes all the items, And some people don't even take any problem solving, for example, or some people don't take numeracy or literacy, or take very little numeracy and literacy. And the question is, how do we give those people a score? Okay? Now, one thing to keep in mind throughout this whole thing is that we're not really interested about individuals. We're not really interested about how one person did on the test. We're actually interested about how groups of people did on the test. That's our goal. Okay? So we use, and at some point someone will ask me a question and I'll say, remember what I said at the beginning? Okay, so just keep that in mind. And if you don't ask the question, I will ask the question for you and I'll say, see, this is what I mean, you know? So item response theory, the first thing that we do is we have to somehow put all the things onto a common scale. And we use something called item response theory. An item response theory does something at the time very innovative, which was before, how do you do in a race? Let's say a running competition. How do you do in a race? And you would say, I came in second, I came in fourth, I came in fifth. And you're like, yeah, but how many people participated? And what was the winning time, right? So it gave you, so before people said, I am at the 90th percentile, but the question is, well, of what? You know, if an item has 75% correct, you want to know, well, who took the item? You know, who makes it 100%? Item response theory changes the way that we report things, and it says, we don't care what the percent correct is, we're going to say your ability, your score, is going to be that which corresponds to the difficulty of an item that you have a 50-50 chance of getting right. Okay, so now we're not saying, and I'm going to draw this because this is literally what happens. So you have items, and you have easy items, and you have difficult items. Okay? You have many items. And let's say I'm going to take these items. So what's the difficulty of this item? Well, you don't know how many people took it, right? Were they able, were they less able? So IRT is going to do something which is, my ability is going to be that which corresponds to a difficulty of an item that I have 50-50 chance of getting right. So,
The 50-50 is the trade-off.
yeah, it's
Lower
a,
because- Lower because of the
if it's lower, then my ability is below that difficulty. If it's higher, my ability is higher than the difficulty.
So this is the threshold.
There's a threshold, yeah, and basically,
Trade-off.
yeah, so basically it says, okay, I think I got right, wrong, right, wrong, right, wrong. So if I take the items and I line them up from easy to difficult, I'm going to get these most likely right because they're easy. I'm going to start failing somewhere around here, and I'm going to fail most of them once I get up there. So my ability is going to be somewhere where I begin to fail to where well, this is an unusual event, but somewhere between here. Okay, so so once you have that, it doesn't matter how many people took the item and how able these people are, but the definition of your ability is not in relation to other people, but in relation to a scale that says, if you take these items, you get this right, you start failing here, and you'll get all this wrong. It's a probabilistic model, so that you're likely to get this right, you're likely to get this wrong, and you'll get this right and wrong at a moderate pace.
And the difficulty is assessed, the level of difficulty, assessed based on
The difficulty is then assessed at the level of which people that have that ability fail the item half the time, fail items like that half the time.
Based on the sample as well.
But it's based on the probability of a person answering that item correctly.
Okay.
Not the entire population, but somebody with that particular ability answering that item correctly. Think of this, because I think this is, it's not percent correct. It's at what point, and then you'll see when you look at the proficiency levels that PIAAC defines, they'll say, this is level 5. And then this will be level 4. And this is level 3, and so on, right? So then they'll talk about those at level 5 are people that are more likely to do certain things than people that are levels below. So the definition of somebody's ability is not with regards to other people, but with regards of the likelihood of somebody doing something that is of a particular difficulty. So in that sense, it's more of an absolute scale than a relative scale. And I'll show you an example later with a high jump bar in the, how so like that works. But once that happens, once we have the items on the scale, we can have other items. And we can have other items. Right? Once all those items are put into the same scale, if I take the green items, or the red items, or the black items, or a combination of the greens and the reds and the blacks, you can also place me somewhere along the continuum. So now, all you have to have is all those items mapped onto the common scale. You give that person a set of items, and then you can map them somewhere in here. Keep that in your head, because there'll be an obvious example of how that happens in real life without us translating it into here. So, response to an item depends on the interaction between the ability of the respondent and characteristics of the item. So, the probability of me getting an item right has to do with how able I am and how difficult the item is. The more able I am, the more likely I am to get the item right. The less able I am, the less likely I am to get the item right. And the more difficult the item, it'll so, what happens is that we have people taking, these routes, and I've talked about this before, and depending on which one they take, they'll go one way or the other. So we want to put all those people onto a common scale, and we also want to score people, give people scores, even when they take few and sometimes no items in the particular domain of interest. So, not everyone takes everything. Task taking is dependent on person's skills. No task is given to a representative sample of the entire population. In other words, those that are able to do the computer stuff, they never see the paper and pencil. So the people that see the paper and pencil are those that are tend to be less able or that have no computer skills. Okay, and then you could argue whether, so I give you the example of my father who's 35, so 70, full turns 79 this year. Very little, he's a lawyer, etc., he can, but he doesn't know how to use computers. He doesn't, he has an assistant, and when I send him an email, his assistant reads it, prints it, and gives it to him, and then he dictates what comes back to me. So, you see, so there's those exceptions, but that's that's part of what we need to take into account here. And he has worked at banks, for his life, and he can do math better than I can, and than any of my brothers, So just by looking at, you give me he's very good at numerical stuff. So, math is dependent on personal skills, don't ask him to represent an example of the entire population. But then we need to put everyone on the same scale, and then compute uncertainty due to measurement, because nobody takes everything. And then, so the question is, you know, and I said my level is going to be somewhere around here, somewhere between where I start to fail and where I stop getting anything right. But there's some uncertainty about that. So, wire response theory, it addresses the limitations of classical test theory, in the sense that the difficulty of the task is defined in reference to the probability of a correct answer, given the ability of the individual. The ability of an individual is defined in reference to the likelihood of a correct answer, given the difficulty of the task. Once a metric is chosen, the relationship between difficulty and ability can be calculated. And the metric is not in reference to a particular population or item selection, but in reference to a relationship between the individual and the task. So let's see.
Excuse me, Eugene.
Yes.
You might just slow down a little bit because we are foreign speakers, so we have to, and it's after their lunch, so we need to. Or is it just me? Maybe it's
No,
just me.
it's not just me.
It's not just me.
It's not just you.
Two of us.
Okay. Any questions about this? Yes.
Just to answer a task and item, is it the same thing?
Yes.
Okay.
Yeah. I mean, I'll say task, question, item. It could be. Yeah. Could be. Yeah.
Okay.
Another question.
Yes.
Is it that finally it doesn't matter if it's a literacy item or a medical item?
The same models are applied to both. We apply the same IRT models to literacy, numeracy, and problem-solving items, but they're different dimensions. So this is the dimension of literacy. There are easy items and difficult items.
And they are not country dependent. They are just dependent. Yeah.
They are. Question is whether they're dependent or not. I mean, all the things are related. So what we do is there's a dimension that we call numeracy. There's a dimension that we call literacy. There's a dimension that we call problem solving. And we're gonna line up the items that belong to that dimension on that dimension. And some items measure that dimension better than others. It's sort of like a factor analysis, kind of. You know, where you have factors and you have items that contribute to that factor. And the same item could contribute to more than one factor. And you do not make them orthogonal. You do not make them not correlate with each other. Is that better? Slower? Yes. Okay, so yes, sorry.
How do you rank the items? Is it based on the proportion of people who are able to answer it, or is it kind of theoretical?
It's empirical. So you basically on the difficulty of the item as it relates to the ability of the people that took the item.
Okay.
So it's an iterative process where you fix the difficulties and then you estimate people's ability and then use those people's ability to re-estimate the difficulties, and then you go back and forth until you reach a solution that's stable, you know, that doesn't change much.
When do you do this process of back and forth?
You do this, to put the items onto that scale, you do that process.
When?
When?
Because you say it depends on the ability of people to answer.
Yeah, well you do, once you administer the assessment,
Yeah.
you get the data from all the countries,
From all.
and then you do that, and then you have the items of a particular, you have the difficulty of the items.
Yeah.
Maybe it's relevant also to mention that the field test, this was an important goal of the field test, testing the the different items and checking how good they worked.
Yeah, so this was on, in the case of PIAAC, it was on during the field test. To select the, to establish, to calibrate, this is called calibration. So to calibrate the items, to put the items onto a particular point in the scale.
And finally, you have from easy to difficult, you have all the items,
All the items, yeah.
more or less equally distant, but
No,
not
I have
equally-
all the items where they fall, not equally distant, but you do want to have easy items, middle items, and difficult items. Usually what you find in these tests is that there's very few very difficult items, and there's more in the middle. But you want to have items throughout.
It is a back and forth process, as you said. At the very beginning, they are all the easy items, they are more or less the same place. All the difficult items, they are more or less the same place. And then based on all
No,
the difficult ones, you can move them, this process of back and forth.
Yeah, so we're getting into more details than we need to, but to answer your question, you basically transform the p-values into logits. So take the log of the odds, and you place them on the scale, and then you take the people's percent correct into logits. And then you do this iterative process where you'll see that the probability of a correct response is given by the person's ability in relationship to the difficulty of the item. And that gives you a probability, and then you see whether that predicted probability from what actually happens. And then you modify the difficulties a little bit, and recalculate and modify the abilities a little bit.
But once the solution is stable, they will be ranked.
Once the solution is stable, they will be ranked, and each item will have a value. Yes.
This calibration is done separately for numeracy, literacy.
Separate for numeracy, literacy, and problem solving.
Because the interesting thing is that when we see the results for each country, there is very much correlation to the results for numeracy.
Yeah, the question is that, I mean, the fact that it's all separately doesn't mean that these are uncorrelated.
It's correlated to.
They are correlated because, I mean, to do numeracy you have to be able to read. If you can't read, it's hard to do numeracy, for example. But the thing to learn here, I mean, I think I mean, there's the technical details, and then it's what you need to know to move on with your life, you know, which is that the items have difficulties, and the way the model works is that if there's this dimension exists, and I start taking these items, the able people will get these items right, and at some point they will start failing, and at some point they will stop getting anything right, and their ability is somewhere in that range where they start to fail to when they stop getting things right. A less able person will start failing at a lower place. A more able person will start failing at a higher place. An unable person will fail from the beginning. And the other principle to take away is that you don't have to give all the items to all the people. If you know somebody's very able, you can get started from here. And you'll see that in the high bar example that I gave you, that if you have an Olympian, then you don't start the Olympian to jump here, you start the Olympian to jump here, and from there up. If you have somebody in elementary school, you have that person start down here, depending on their height, their weight, etc., etc. So, and you can then compare the student from the high jump ability of the student in elementary school with that of an Olympian, once you have the scales on the same metric. So I don't have to jump, I cannot jump this high, but I don't have to jump this high to be able to compare with the Olympian. So different people taking different items that are in different places will get ranked onto the same scale.
For instance, in the low part will be mainly people who participated in these reading tests.
In the paper, yeah, for the most part, not exclusively, but for the most part, yeah. Yes?
Is the calibration done for each country separately, or is it for the
No,
whole
there's
country?
one common calibration for all countries.
But-
So you put all the countries together,
Okay.
and then you calibrate the items.
But is it possible that in some countries the ranking would be different?
It is possible that, so two things happen, okay? Just like I say that that there's some uncertainty associated with my ability. There's also some uncertainty associated with the difficulty of the item. So who are the ones, where's the difficulty of the item? The item is where, somewhere in between where, so there's some uncertainty about that. I'm trying to come up with an example. I'm getting confused myself, but the difficulty of the item will be somewhere around here. And my ability is somewhere around there. So my ultimate estimate is going to be dependent on the difficulty of the items that I took and the discrimination of the items that I took. So that difficulty could be somewhat different country by country, or it could be very different in a particular country or a set of countries. In which case, in the case of PIAAC, what they do is that they might treat that item as separate in that country, so that item will get its own, so it will show up here for everybody, and then for the, from the Czech Republic, it will show up here for the Czech Republic, or down here.
Yeah.
But that would be the exception, because if you have that happening too many times, then you actually don't have one dimension, you have a dimension in the Czech Republic, and a dimension in Norway, and a dimension in Australia, and a different dimension. So you want to have most of the items to have the same difficulty level across all the countries. Yes.
When we do the second phase of PIAAC, where some new countries will participate, shall we keep the same calibration?
Yeah, so that's a good question. So the question is, when we do the second phase of PIAAC, what happens with this? Well, once this metric is set, this metric is set. This is the metric. So the countries that take PIAAC later will use this metric. Same thing in PISA. You know, the metric, this metric is set with the OECD countries. So then you have the 30 plus other countries that take PISA, and then the metric that they get measured with is the metric derived using the OECD countries. Better? Yes? No, good. I'm glad that you did that, because sometimes I might, so. Okay, so take away from,
Is the difficulty reported everywhere, anywhere? The difficulty of the items?
yeah, it's reported in the appendix of the technical report.
Perfect.
Yeah, there'll be a, with all the item parameters. So this is alright what happens, you know, each item gets a curve that looks like this, you know? Where, here's what I'm saying, the more you have of that latent trait, of that thing that we're measuring, the more likely you are to get that item right, and at some point, you'll be more likely to get it right than not. And as you see, the green item, you need more ability than the blue item, and for the blue item, you need more ability than the red item. So the more of this you have, the more literate you are, the more numeracy skills you have, the more problem-solving skills you are, the more able you are to get that item right. These items have different levels of difficulty, and these items also have different slopes. So this item is easier than the blue one, but here it becomes more difficult than the blue one. Okay, so these lines could intersect. If you have a multiple choice question, then you could also say that really the chance of getting the item wrong is never zero. It's never one, because when you have 4 choices, you can always pick one at random. So you'll see that in some cases, this line will never be 0. So it will go at 0.2 or 0.25 or something like that. So we come up with a function for each item that describes the relationship between the latent trait, literacy, numeracy, problem solving, and the probability of getting that item right. And then, depending on which items the person took and got correct, then we'll try to place them somewhere. Here's what happens when we have items that are worth 2 points. That the more you have, your probability of getting a 0 decreases, and the probability of getting 1 point increases. And at some point, you're more likely to get a 1 than to get a 0. And at some point, you're more likely to get a 2 than to get a 1. Okay.
Say, what are
Huh?
P0, P1, P2?
Probability of of getting a score of 0.
Ah,
Probability you're getting a score of 1. Probability you're getting a score of 2. In the case of a 2-point item, so it's 0, you can score 0, 1, or 2.
so it's an item, 0, 1,
Yeah. The principle again is the same, you know, is that the more you have of this, the more likely you are to get the higher score.
I guess not all items are that balanced, because this one seems to be pretty balanced.
Yeah, well, I'm just doing an example. But this is how they usually look. About good items look like this.
Most of them,
Yeah.
because this is a kind of healthy behavior.
Yeah, this is a healthy item. Yeah, this is a healthy item. So it facilitates dealing with multiple matrix sampling because each person receives a subset of the items, and each item is administered to a subset of the people. And then the total score is based on the characteristics of the items taken, not on the percent correct. And here I have the example of, you know, in the high jump example, you can jump 66% when you jump 205 and fail 210. And that's very different from this 66% where you jump 150, 155 and fail 160. Right? This person jumps higher than that person. Some of the advantages of questions? Okay, some of the advantages of IRT. It allows us to evaluate the effectiveness of a test at different levels of ability. You know, think of once you have these items ranked, if you want to select people that are at level 5, you give them these items. You don't need to give them these items, right? If you want to screen people at level 1, you give them these items. You don't give them the high items because it's unnecessary. Okay, so it allows you to select items for a specific purpose if you place them correctly throughout the continuum. Evaluate the set of items on a scale established by a different set. Design tests to measure best at specific ability levels. Develop new tests and investigate them without administering them, etc., etc. So it allows you to, once you have those items calibrated, you can make up your own test to measure something at a specific level or at the distributional level. So here's what I have. Any questions about this? Okay. So how high can you jump? And here in the example, because I think so like illustrates, you know, that here we have one high bar in the United States, and here we have one here in Europe, and this is in inches, this is in centimeters. Right, so the first trouble is if somebody jumps 70 here, what is that 70 there? So you have to put them, make that 70, 70. Okay, so you convert the centimeters to the inches. I use this in America, so that's why it's, I went that way, I could go the other way. You know? But then the issue is, so once you have these on a common scale like that, then you can, if you have a short guy like this, and the question is, should he jump this one or that one?
It's a she.
It's a she, why? It's a he who's wearing a cape. I don't know, this individual. Which one should she jump, this one or that one? Right? And you would say, well, most likely the one on the left, and you get somebody like this, and then you're like, well, maybe this one, maybe that one. You see? And you get somebody like this, and you would think that one, but that person could be injured, etc., you know? So it allows you, based on what your assumption is of the people, you can design a test that would answer the question, how high can this person jump? Now, if you give this person this one, and they clear 80, How high can this person jump?
Maybe more.
You don't know. They can jump 80, but do they stop at 90? 100? You don't know. And same thing. If you give the little guy this one and they don't jump, how high can she jump? You don't know either because they didn't clear 60. So you know they're below 60, but you don't know how. Now let me ask you another thing. So this person jumps 80. How high can this person jump? They jumped 80 and they failed 90. How high can he jump or she jump? Somewhere between 80 and 90, exactly. You don't know. Because you have imprecise measures, right? If you take 1,000 people, that jump 80 and fail 90, and you give all of them 80, what happens? What's wrong with that? You're underestimating the height that people can jump. And what's another problem that you have? The distribution of people of jumping abilities will be also incorrect. Because people will jump 80, 81, 82. All those people that jumped 80 can jump all the way to 89.99. So if you wanna report about the individual, then they jump 80. If you wanna talk about the distribution of the population, somehow those people that jump 80, you have to spread between 80 and 90. Somehow. Okay? So, item response theory, persons of high ability answer easy items correctly, persons of low ability should not answer difficult items correctly. This is sort of like the expectation of what always happens. Let me mention another thing that is important here, an important difference between how high can you jump and giving a score on a test. How high can you jump has to do with the maximum height that you can jump. Okay? In this case, how high can you jump will be that. It's an item of the most difficult that I was able to get right. In education, in tests, what we're saying is, what are the items that the person has a 50-50 chance of getting right? So it's not which is the most difficult item that a person gets right, but what is it? What is the level where the person has a 50-50 chance of getting those items right? So it's a different concept. But behind the scenes, it's like the same principle that we're trying to rank people on this dimension, and we make them take tasks or items or questions that have a certain level of difficulty, and based on that, we will place them in one place or another. And we have to fill in the gaps also. Persons of high ability should answer items easy items correctly. Low ability would not answer them correctly. The probability of answers depends on the item parameters and the ability of the examinee. It does not make assumptions of normal distribution, but assumes unidimensionality of measurement. So it assumes that there's one dimension, and you can place those items along that dimension. So, achievement is initially estimated using scale scores, computer based on IRT, which allows us to put things on the same scale. And then we use something called plausible value methodology. So, plausible values are random draws from the estimated ability distribution of students with similar characteristics, similar item response patterns and background characteristics. Think of a regression where the predictors are item responses and background data. Okay? Think of that. Think of the following. Think that meters, 80 inches. 90 inches. Okay? And I have 1,000 people that jump 80 and they fail 90. Where will you place them?
In between.
In the middle. In the middle.
In the middle? Will you do, okay, let me ask, will you do something like this?
Normal distribution.
No? Will you do something like that?
Yeah.
No? Will you do something like, possibly, yeah? So this would make more sense, right? Because you would assume that of those that jump up to 80, most will jump 81, but then they'll start dropping off, right? Yes? Fewer and fewer. Okay, so those 1,000, when you're going to spread them across there, you will not put them all here. You will not put them all. So let me get the other. This is why colors are good. So you wouldn't do. You would not do that, right? So you would go. The winning one so far is this one, right? Yes. Approximately. We don't have to be exact, but you would do like that. Now the next question is, okay, so how do we put them? How do we place them like that? So yeah, okay. So you can jump 82, 83, but we wanna spread them across. So now I have to guess. So you have stand up. So you have him and I, right? We both clear 80, and now you're gonna place us somewhere around there. So, should he get a higher score or not? He's taller, he should get a higher score, right? So, okay. What else? So, because he's taller, chances are that he will score higher, right? What else will we look at?
I guess it's what you said, background.
Background information. So depending on who he is, you know, height, weight, age, training, athletic ability, etc., etc. When we both clear 80, if you were to predict where people like him would place and people like me would place, just using the tall information, you would place him higher. Using other information, you might place me higher, you know? So, the people that are here, that jump 80, the question, how are they gonna spread throughout here? It could be also that even somebody that jumps 80 and fails 90 just had a bad day. And they could even jump higher than 90. But they just, that day, they couldn't. And it happens, you know, when you see athletes in the Olympics that they don't jump as high as they jump some other situation, right? So the question is, when you're trying to describe the population or the jumping ability of people, where do you place him? Where do you place me? And when you're estimating the distribution, let's say that you have him and you have a female. Same height, same background data, except that one is male, one is female. What would happen? Who would have a higher chance of jumping higher?
Men. Men.
Somebody says the same,
No.
somebody says male. But statistically speaking, males jump higher than females,
Yes.
right? For whatever reason that is. So if you have 1,000 people, 500 females, 500 males, you would be more right. You would be right most times if you choose the male jumping higher than the females. Why do you say that? Because you look at their world records, you look at the Olympic standings, you look at all its competitions, and males jump higher than females. So based on that, if you were to assign a male and a female that show up here, the same number, 1,000 times, it'll be a good thing for the individuals, but when you're estimating the population, you will be doing a bad thing. Because you will be, not representing differences that exist between males and females. It could be, by weight, I mean, male and female is controversial because people think, yeah, we should jump the same. But let's say that somebody's heavier than the other person. The heavier person will jump less than the lighter person. So if you have two people and you know their weight, if you were to guess, you will guess that the lighter person will jump higher. You happy with that? So, exactly what we do here, where we have people taking items, and those people that have this ability, sometimes they get that wrong, sometimes they get that right and that right, so sometimes we get things that are above our ability. Because, again, remember, the ability is where we have a 50-50 chance. Okay? It's not the highest, not the most difficult, but where we have a 50-50 chance. So you give people more items, and those people that show up here come from somewhere. Could be people that are lucky or unlucky, getting that item right, those items right. And sometimes the people that show up there could come from two distributions. If you flip this and put it there, it could be the distribution of heavy people and lighter people. Long legs, short legs. Okay? But we just don't know because him and I only cleared 80, so you just don't know. So what you do is you literally say, okay, the distribution is like that, and then you say, yeah, but the distribution for people like him is more like this, and the distribution for people like me is more like this. So from this distribution of possible scores, you give him 10 possible heights that he can jump, and you give me 10. Sometimes he will get a score lower than these are not proportional, so disregard the proportionality here. But sometimes he will get a lower score than I do, and sometimes I'll get a higher score than he does. But on average, over multiple tries, he will get a higher jumping height than I do, just because he's taller than I am. You can add to that age, and you can add to that weight, you can add to that other measures and improve your prediction of that distribution. Believe that? Yes? Anybody doesn't buy that? So there's two main principles here. One is that there are difficulties, and based on how we do in those difficulties, we get placed. But then there's some uncertainty, and then we're going to use background data to help us with that uncertainty. And
Are the plausible values in the public files?
correct.
Or do we compute them ourselves?
No.
They are already computed. They are in the files.
They're in the files, yeah.
Yes.
These are in the files. So plausible values are, yes, they're in the files. There's 10 of them in the case of PIAAC. They're optimal for obtaining population estimates. So if you were to choose us, although we do that in real life, but if you were to choose us to make it into a team, for the Olympic team, you have to jump a certain height. If you jump it, you're in. The coach shouldn't be like, oh, maybe, when using plausible values, so then we have, each one of us has 10 estimates. So to compute the estimates, you would have to compute each estimate separately with each possible value, and then you will report the average of that estimate. And then you compute the variance due to the measurement, due to the imputation, which is going to give you your certainty about the measurement of the people that are ranked in that scale that you have there.
So in the files, they are item by item, close.
No, the file has 10 for literacy. There's 10 different values for literacy. There's 10 different for numeracy. There's 10 for problem solving.
Okay.
But also some.
No sum. There's just 10 different ones. And every time that you're going to do the analysis, you have to use each one of them separately. So
But these are plausible values.
yeah.
Though the computation has,
Yeah, all that has been done already. So if you look at the let's take a look at the file here. This is the file for Norway. Well, let's take a look like this. So this is the problem solving for the first record in Norway. So you have 225, 249, 235, 220, 214, 250, 226, 237, 265, 243.
And again, what are they? 225?
Those are the plausible values. Those are the scores that we gave the first person in numeracy, in problem solving.
And why are they 10 scores? It's just a choice.
Because we're selecting from the distribution. So the example I said before, so you and I cleared that, and then based on your background, the distribution of people like you is like this,
Yeah,
and people like me is like that.
okay.
So but you don't know where you fall because you cleared that. So we'll take 10 numbers between 80 and 90 with probability proportional to that distribution.
Yeah.
So you get 10 possible jumping heights that you could jump, and I get 10 possible different ones.
but for this first record,
Uh-huh.
this could be a plausible value, and it could be, or we don't know. Or is it the exact value, the exact as this person achieved? Or
We don't.
or might it be? It could also be a plausible value for
No,
this
It's
person. Or
it's always a plausible value.
it's always a plausible.
Always a plausible value. Yeah.
Okay.
It's not a sum correct, it's not a percent correct. It's always a plausible value.
But what do you exactly mean by saying that plausible value should not be used for individual reporting? Because we never report anything for individuals.
Well, some people try to do that. I mean, some people wanna, and in the adult studies, no, but when you have at the school assessment, they wanna give each student a report and say, here's what your child,
Oh,
yeah.
yes.
I mean, I had, when we released the results from TIMSS in 1999, I had a reporter come me and said, who was the highest scoring person in the US? And which school does he go to, or she go to, you know, where's the student? And so you have to explain that even those that score perfectly, you still get 10 different numbers. In PISA you get 5, and in PIAAC you get 10. But the thing to learn here is that the key thing here is that you compute the statistic with each possible value and then average the results.
So whenever you build a statistic, you need to do it 10 times?
Every time you do any statistic with possible values, you have to do it 10 times. You don't have to, you should do it 10
You
times.
should do it.
Yeah.
And then you average.
And then you take the average of that.
And the variance is that.
And the variance is this, which is the variance of the results, of the 10 different results, multiplied by, this comes to be 11 over 10 here. So, hopefully this will wake you up. I just told you, he said it, I didn't say it, that you have to compute everything 10 times. And to get at the sampling weight, you have to compute everything 81 times. Okay? And you have to do, if something involves possible values, then you have to do it 81 times for every possible value. So that's how many? 810. So anytime you want to get at an error of a statistic that has a possible value involved, you have to compute that statistic 810 times. For PIAAC, yes. Okay? But that's why we have computers. I mean, that's why we have computers. That's why we have the idea. You know. I want you to get the principle here, you know? And I want you to get the principle, and I want you to understand the consequences of not doing that. Also. Let me, well, let me give you a couple of examples. So we talked about this. So, you know, when you have something that don't involve the possible value, then you have to do it 80 times. And here you do it 80 times times the 10 possible value, and then the 10 possible values here. What happens if you don't take this into account? And then here's two examples of what happens. You know, number one is, here you have a difference between boys and girls in New Zealand in TIMSS 1999, and the difference was 8 points. And the question is that difference statistically significant or not? And if you ignore the last 2 hours of my talk, you'll say the error is 2.9, and you'll say, ha, there's a difference between boys and girls. Girls do better than boys in mathematics. And I'll be like, hold on a second. If you use the complicated formulas that I presented there, your error is actually 8. So a value of 8 with an error of 8, not significant. Okay? So let me show you. Any questions about this?
Why this choice of 10 plausible
Why the choice of 10?
and then pizza 5?
So question, why a choice of 10 and not 5 like in pizza? And what happened is that as time goes by, we can do more. Because computers are better, there's more storage capacity, etc. So basically, the 5 comes from back in 1983 when this technology was first used. And it was very expensive to store all that stuff. So somebody said, okay, 5 is like the minimum that we should have there. Now,
10-year times they will be 10.
yeah, actually in NATE, the National Assessment for the US, they're doing 20 this year. For in 2013, they did 20. But which means, you know, that instead of 800, it's 1600 times that you have to do the analysis, you know. So then, at some point, you're like, what am I gaining and what am I losing? Let me give you one last example. Okay, so here's what you all know regression, right? Yes? So we know that in regression, we have y equals a plus dx plus an error, right? And we know that the y hat is equal to a plus bx. Okay? So here's what I did then. I have an x and I have a y. And that y is equal to d3, which is going to be d3, the constant there, plus a10, so x times e3. So that's my slope, my constant and my slope, yeah? So I'm basically saying there that y is equal to 10 plus 5x plus an error, which has mean 0, standard deviation 5.
Yep.
Yes? So that's what my y is there. And then I use Excel and I compute. So I create I check this and then I estimate, and I get, Excel tells me that the constant of that regression is 10.2 and my slope is 5. 5.06. So y hat equals to 10.2 plus 5.06 x. And I say, okay, so I have my y hat. Here I plotted x with y. And now I'm going to plot my x with y hat. How does that compare to that? Let me ask you this in a different way. Does this reflect that? It's the line of best fit, but what's happening here? And somebody here,
It's just the error that we introduced.
everyone that gets a 10 gets the same score here. But in reality, everyone that gets a 10 gets a score that's distributed with standard deviation 5. So yes, this is the line of best fit, but this doesn't represent what the population is. Doesn't represent the true relationship between x and y. Yes? So let's hold that thought for a second. And then what I'm going to do here, and that's because there's this residual, right? So I'm going to construct this y hat plus. And what that y hat plus is going to be is going to be my C10, so it's my y hat, plus I'm going to add a normally distributed error. We have mean 0 and standard deviation E7, which is that error that I found there. So each case here is going to get a random error assigned to it. And that's going to be my y hat plus. Look at my y hat plus. I would say that that looks more like that than that, right? So adding uncertainty to my numbers, you could say it's unfair. The line tells me that those who score 10 should have 60 here. But I'm saying, well, yeah, but in reality, those who score 10 are somewhat spread between 50 and 70. So I'm going to do that, and this graph represents that better. And if I do that over and over again, you will see that that will be, so every time that changes, that's one possible value. Which one is right, which one is true, I don't know. So I'm going to do that 10 times. Treat them separate, as separate estimates. I'm going to take the average of those. Notice another thing that happens. That the standard deviation of y hat is 8. Standard deviation of y is 10, 9.9. So if I do the y hat, if I do that over and over again, that would always be lower than that. Lower, 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 lower. Now, the standard deviation of my y hat plus will be closer to my standard deviation of my y hat, my sy. So, while the means don't vary, the variance will be underestimated if I don't do this. Yes. And another point here that I want to sort of like address is that so people say, so why not take the average of the possible values? Because taking the average will be taking that again. And taking that, I've shown you already that that doesn't look like that, and that underestimates the variance of y. So, if we want to get a proper estimate of the variance of y, and we want to get a proper description of the population, we're better off doing the analysis separately with each possible value, and then taking the average. So this, I thought I had added questions about this?
This slide in the archive that you provided to us,
No, this one not. But I can send it to you. I'll put it.
it's very useful.
I will add it. I had an example here. So why is this important? So here's some questions that you want to ask. You want to do a regression analysis using predicting literacy or numeracy or something like that, or using numeracy or literacy to predict something else. Okay? So the question is, how do you do the regression analysis? You would do it once with each possible value. And one of the things that you will find in some cases is that with one possible value, if you do a stepwise selection or forward or backward selection, that different variables will be selected, or there'll be a variable that drops in and out. So what's the answer? The answer is you need to force enter the variables, and the variable drops in and out because of significance. So if you want to know if the variable really belongs in the equation, you run the regression 10 times with the variables that you want in there, and compute the errors using the formulas that I gave you, and see whether the variable belongs in there or not. So, the other typical question that people want to ask is, we want to select the people that are, this was one that came up a lot, we want to select those that are low numeracy and low literacy. So, how do you do that? You have to select them with the first possible value, then with the second, then with the third. And every time you do this, you'll have a different selection of people. So, to give you another example, which I thought I had added to those slides, but I didn't. Here's I classify people with the first possible value in literacy and with the second possible value in literacy. And we have that for many cases, you could be classified in one level with the first possible value and in a different one with the other possible value. So which is right? We don't know. And because we don't know, that's why we do it 10 times, and we figure that on average, we will be right. But in any one instance, we don't know. So we do the analysis 10 times. If you're going to classify people, you classify them 10 times. When you look at the percent of people at each level, you classify them with each possible value, you compute the percent, and then with the next, and you compute the percent, and the next, and the next, and then you take the average of those.
So you want to do a regression with a set of predictive variables, you want to predict something like literacy. You want to use all 10 PVs, do the regression analysis 10 times.
Correct. Yep.
Average the results. But from your earlier, before lunch, we were talking about the BRR with phase. So where does that come into the...
That comes into place because you're going to have to do that regression. So the question is, if you're going to do a regression predicting literacy, so you do that once with each possible value, that's 10 times, and then you should do it once with each plausible value with each replicate weight. So you're going to be computing that regression 810 times and summarizing it using the formula where the formula with the F. Two things, the formula with the F. Let me go back to where I should be. Here. So you'll be summarizing the 10 results here, and then the 80 times 10 results here. I'll let you speechless, huh?
Yeah.
But this is why, this is what the IDD analyzer does. You can program this in Stata, I assume, when you do the data export, you can do that. So that's why we don't make money in these tools, but we're pushing it because that's the way to do things the right way.
Or in the Australian case, the Australian Council for Educational Research, which held some of the OECD data sets in the past, would write the syntax for secondary researchers.
They could, yeah.
And then distribute it.
Yeah, so you could do, there's modules that they prepare to do that, You look disappointed somehow, or disheartened. It's not as, it's complicated, but it's doable. So, and it's been done for many years, so you're not the first, the only ones, or the last people trying to do this, so it's doable. Questions about this, about sampling and about this whole thing with replication, multiple imputations? Yes, huh?
I suppose that you have to use the same procedure even when you use the skills, different types of skills, as the dependent variable or as an input as an independent variable.
Yes, yeah. Whenever you use the plausible values, that's the way. If you're not using, so I'm not sure why, I think there's some question about using skills in the workplace, If it doesn't involve plausible values, then you use the top formula.
It doesn't have to be only skills in the workplace, but skills level.
Yeah.
At skills level as an independent variable, explaining
Yes.
output. For instance, wage.
Yeah.
Which is done in several papers already. I've seen.
Yeah, and here.
Well, not in several, but 2 or 3, I think. And where they have used.
Yeah, it's been done, and one thing that I'll say is that
I suppose they have used your.
I don't know, and I do know that many times it's not used. This is not my thing. This is how, if you want to do this right, this is what it is.
Yeah.
You see a lot of people, you see papers written and approved and reviewed and published without doing this. You see people presenting, and very famous people presenting and talking about the stuff without doing this.
Okay.
So it's not a matter of, you can get away with doing it many ways,
The last time I was attending the Washington session, and there was sitting next to a statistic wizard, and he said that he has tested both with and without using and not with not using, and he said that you showed us an example where suddenly the error became,
Right,
the
yeah.
difference became statistically significant. But he said that there's very little difference in reality, like in social sciences, in practical terms, the difference, okay, unless it's not on the threshold, so,
Yeah, but how do you know?
yeah, exactly. By doing both.
Yeah, I mean, I think we're not talking about, I mean, I mean, it's sort of like I don't know, I mean, I think there's always a dilemma, do I do it? Do I do it and get it done with, or do I do it right, I think it's yet another noise and yet another piece of dirt in what we're doing, So, I say we're not putting planes up in the air, so the things won't crash, But if you were in an airplane business and you said, let's just use one PV and the plane crashes, they'll come and chase you and put you in jail. For negligence, for being, for negligence basically. So nobody's gonna go chase you and put you in jail. We may laugh. At you maybe, or we may say, but I think, I think you need to make because I think there are consequences to what we do, So, and that's, I think the consequence sometimes diffuse, and that's why I put the example of the airplane. If an airplane crashes, we were like, how could this happen? And we go, and it's amazing the amount of care and amount of information that gets recorded about an airplane. And what they get at. It's like their maintenance records. And in our field, we can skip a lot of things, but there are consequences. So somebody was asking us to, they want to do school reports. They want to give, using the PISA 2012 data, they want to give school reports. And then you could do it using one possible value. You can take the average, you can ignore the sampling, the variance estimation, and there are consequences to doing this, because a school that was in the threshold then underperformed is not going to get something that they should have gotten, and a school that falls on the other side will get something that didn't really quite belong to them, So I think nobody's going to die, no plane's going to crash. I hope. But
and another thing is that the reviewers of the articles, we are privileged, we have the knowledge and on the level of
Yeah.
details, but the reviewers in social sciences of those articles, are they on that level? And
no, they don't.
I mean,
how would they find it out? They would have to run the analysis.
They don't. Yeah, I mean they don't. They don't, and you see what people write, and they don't. And even when I review papers, and other things, sometimes I do ask and say, you gotta make sure that this is stated explicitly, but you, in the end, you don't know, and the editor at the end might say, might or might not understand the issue fully, and might ignore my comments, even, so. But I think there's a, it's sort of like a moral thing, unquote, I mean, I don't want to be preaching here, that bad person, but these are the rules of the game, and this is what this means, and then when we say, some of you will be trying to do analysis, trying to predict likelihood of something, people want to do logistic regressions, and that you'll be predicting the chances of being in one place or another, Well, all these things matter when you're making that prediction, so if you become famous and say, because you discover that if you did this, the chances went from A to B, then somebody eventually might check, or somebody might not check, to see whether that difference is really statistical. I don't want to scare you, but I think that this is the way in which things should be done. This is the way in which these are designed, these are the rules of the game. And there are tools to do the things, nowadays there's more and more, I meant it when I said I've been doing this for 20 years, the tools that we had then are nowhere near what we have now, now you can go to the web, click, click, click and get the numbers, you know. I'll show you that software later, you know, tomorrow.
And of course, we want to get things right. I mean,
Of
it's
course.
not to say that, you know, why bother, but,
No, I know.
yeah, so.
Yeah, I mean, I don't wanna be like the priest, like, you know, you're gonna,
You probably should be. You probably
yeah,
should.
burn in hell if you don't do this, burn in statistical hell,
Yeah.
you know, but, no, but I mean, I do think, and as I said, and you know, there's very famous people that don't do this stuff, and they're famous nonetheless, and they get, you know, very famous, so. But at some point, there's a level of honesty in a way, you know, like this is the way that, if you don't do this, you shouldn't be making those statements, you know. Nobody will question you. And we do get often, you know, but so-and-so does it like this, why do we have to do it? I'm like, so,
And
yes.
another thing, when you use the plausible values, you always use plausible values. But you do that both for persons who haven't been tested and also for others. You always use plausible values.
Okay, good
So
question.
you have imputed plausible values for
Yes.
persons who haven't been tested.
Exactly.
You haven't talked about.
So this guy right here, right,
Yeah.
he didn't jump. He didn't jump. And the question is, how high can he jump? Right? And you say, well, I don't know. But you do know people, his height, his weight, his age, his country, all these relevant variables. And you can take a you can make a very good estimate, a relatively good estimate of how high he could jump, and you could say, well, given that, well, they both work at the European Commission. They both are about the same age. They both wear glasses. You know? And if those variables are relevant, then you would say, well, he would jump like that. So for him, because he didn't jump, you would draw scores 10 from here. Because he jumped, then you would start up here. And it's what we do when we select any one of you that professors that select students. If you have selected people for a job, the question is, how will they do the job? And based on the test scores, based on an interview, based on sometimes on, hopefully on relevant variables, you will pick a person over another. Typical example, if I have two players, one from Venezuela, where I'm from, and one from Germany, and I make it do drills, so in football players, and they both do exactly the same, which one will you pick?
Where's the game going to be?
Here. Which one will you pick? Good question. Which one will you pick? And why?
I'll pick the German,
Why?
because the conditions are more familiar.
But they have the same skills. What do you mean they're...
Well, if the game was in Venezuela, the context would favor the Venezuelans.
Maybe, yeah, okay.
There is opposite. That Venezuela may not have been trained up to his potential. So that would
Maybe, yeah,
require that in Germany is up to his potential. So
maybe. But if you were to pick, if I were to present you, so that's one case, right? If I were to present you 1,000 cases like that, which one will you pick? I would pick the German. Because over multiple choices, I will be more right than wrong. So in any particular pairing, the Venezuelan might be a better player than the German, but over time, over multiple picks, the German will be better. Why? Because in general, in Germany, they play better football than they play where I come from. So not knowing anything else, knowing their skills and knowing that one is German, one is not, I will pick the German. Statistically speaking, and then again, we're here, and here's where I was saying before where I started this. We're not out to make fair comparisons of two individuals. I'm here to describe the population. And on average, German players are better than Venezuelan players. So if I were to pick Germans between a German and a Venezuelan football player of the same set of skills, if I pick the German, I will be more right than I would be wrong. Or multiple picks. That's how people win blackjack. That's how the casinos make money, because in any one interaction they'll be wrong, but over multiple interactions they will be right. More than you. So that's all like what we're doing here. So, any more questions about this? Yes. Huh? Dozens, yeah.
What about the people that answer to a small set of questions?
Same.
Three, two?
Yeah, same.
Yes, it's the same?
You don't have to answer anything. You don't have to answer anything. You do need to have, and it's funny, but yeah, I mean, you don't have to answer anything. You do need to have enough information about the relationship between the background data and the thing that you're measuring.
Yeah, so the background data, the background questionnaire has to be filled in.
Yeah, you need to know,
Yes.
yeah,
But
Have
not
a
even the
complete
core,
case.
the core,
yeah.
not even the core questions, but.
You have to have, in this case, you have to have taken the core. In the case of, yeah, in the case of PIAAC, you have to have answered the core question. But if you look at what PISA does, for example, some people, and what we do in problem solving, some people don't take problem solving at all. And you will still include the value, because we know who they are, and we know how people like them do in problem solving. So we can make a relatively good guess of their distribution of scores, about where they will be in the distribution of scores for problem solving. Again, think of the example of hiring an employee or hiring a student. That you don't know what their performance is as an employee or as a student, but based on past information, based on experience, you make a pretty good, you can make a relatively good guess, better than picking a random.
Which, just only to be sure that I understood, which is not the case for PIAAC, because the guy that didn't jump, we will never assess him by himself. We will only participate in that average that we will produce at the level of the sample.
Yeah, sort of, yes. Well, at the level of people like him, for her. So, I have an individual, me, and you want to say, how high can I jump? And you'll
He
say,
didn't jump at all.
right, and I didn't jump at all, and I'm not going to jump. But I want you to guess how high will I be able to jump. And you say, okay, are you a male or female? A male. How tall are you? 168. How heavy are you? So based on, so I'm a male, you say, okay, you can jump a little higher. I'm a short male, so you a little lower. I weigh 70 kilos and a little lower. I'm almost 50, you jump a little lower. See, it's like, my knee hurts, a little lower. Or my knee doesn't hurt, a little higher. I'm in good physical condition, a little higher. So based on that, and basically, you follow that, right? So depending on those things, you have your ability is a function of your background data plus an error. Your background, well, let me do this. Let me do this fully. Your data, your ability is a function of your item responses plus your background responses plus a residual. So you have a whole bunch of parameters here for the items responses, and you have a whole bunch of background parameters here. And you can then compute that based on what happened there. And then at the end, you will say, well, given that, you know, then I'm gonna be here, plus or minus something. Which is to measure that residual over multiple cases. So you say, okay, so I'm gonna pick from here 10 numbers.
And I was saying that you produce those 10 numbers, which are the 10 plausible values for that individual.
Yeah.
But then, when assessing at the level of the whole sample, you calculate the means for each of the 10 plausible values.
Right, yeah.
And then you estimate the whole sample, but you never say something as a whole about that guy that you didn't jump.
You never say something about that guy.
It was
Exactly.
a difference.
Yeah, you have records there, and they all have numeracy, literacy, and problem solving scores.
Just a question, is it true that the more people that they didn't jump you have in the sample, the higher the higher the variance?
Yeah, basically, yeah, yeah. So the more, so we don't make up the stuff, you know. So the fact that we give people problem-solving scores that we have, I think it's like, I forget the number, but it's like half of the population or so does take problem-solving, and we know that the relationship between problem-solving and numeracy and literacy is 0.8, 0.7, something like that. And we know that the relationship between problem-solving and the background data is, depending on what you put in there, is something, you know. So we can use that information to then estimate where in the distribution that person will. But you need. So we don't say females should do better than males. We look and we say females do better than males. Here we have a male. Should we give him a score and a female? Who should get the higher score? On average, he should get the higher score. It could happen the other way, that we see females do better than males, and then we'll say who should get on average, he should get a higher score than him. Yes.
In the field test, we had some cases where, because of the duration of the questionnaire was very, very big, but the background questionnaire was filled in, was added already, and then at the assessment, we had just zeros. They just passed the PPAs or the CPAs, and they did nothing there.
This is in Greece?
Yes.
On
Yes.
PIAAC?
Yes.
Uh-huh.
In the field we had some cases. We had all zeros in the assessment. So, in fact, according to this type there, we have to fill the ability just from the background questionnaire.
Yeah, and remember that there's some rules, you know, that I mentioned before, that you have to pass the core.
Yes, yes.
So-
Yes. Oh, okay.
Yeah, so you have to pass the core.
Yes. To be able
And
to
then-
do the case. Yes.
And then the question is whether, see, there's two different things that could happen. Whether some people might have said, I don't know this, in which case they should get zeros. Or the person could say, I don't want to continue with this, in which case,
Yes, but they don't say I don't want to continue, and they, for example, if they are in CBA, they just click the next one, the next one, the next one, and
Yeah.
the time is a parameter that has not been taken into account.
yeah,
And for example, in this case, I suppose that, for example, if he has a PhD, then the score for this case will be very high, for example, because of the background questions.
yes, it would be higher than somebody without a PhD, even though they didn't do anything, yeah.
Yes.
Because if you were to guess the score, if that person had gone through the whole activity, you would be, over multiple times, you would be right at giving that person, on average, a higher score than somebody that with less education, yeah. So in one of the last sessions, there was a link to the PIAAC Data Explorer. So let me go through this by myself first, and I want you to watch. Because what we're going to do is we're going to access the server at the OECD, and if we all do this at the same time, it will slow things down quite a bit. And I know you're tired, I'm tired. So let me do a demo of how these things work to give you an idea. And then you have time to do some things. And then tomorrow we'll practice again. You know, it's something that will, you know, take some getting used to. But this is a tool that is available at the OECD, at a website, and then you can run some analysis. Not everything, but you can do some things. I think my computer thinks it's on vacation in Prague, so sometimes it slows down. And
No, in fact, I think the Microsoft PowerPoint is blocked, so you need to close it and open it.
it's blocked by.
It's not that, I don't know.
Yeah, there you go.
I was wrong. It's not blocked.
Okay, so here we have something that looks like this, right? And so you can select the subject, meaning you can select the domain that you want to work with. So here you cannot cross numeracy, literacy, and problem solving. So let's take literacy. And what you find here is that there's it'll tell you the skill scores that you can work with, and then you can do, let's do PIAAC literacy. You can click here on details to see what it is. You can hide details or see the details. By default, it will select PIAAC 2012. You can also select the all or the IELTS. I'm just going to do PIAAC for now. You can select OECD national entities. So you can then select, you know, you can either select here and select them all, or you can select country by country. I'm going to select them all. You have the option of selecting the OECD average, meaning the average of the OECD countries, or the average of the selected countries, or both, for a table. Then the next step is to select variables. So let's select something simple. Let's do something creative. Let's look at gender differences. It's a new, unique question that nobody else has looked at before. And let's look at gender differences. And then let's do highest level of qualification. And here you can click on details. And it's going to tell you that these are the codes. ISCAT 1, ISCAT 2, ISCAT 3, etc., etc. So I'm going to select those two variables. You'll see some of you were asking about employment status. So here's current work, current status work. So background, born in country, age groups. So you can select multiple background variables that you want to analyze. And then you can edit the reports. And here you have, I mean, you can do multiple things here, you know, but you could edit and you could select the statistics that you want to see. So you want to see the average literacy, and let's say you want to do, you can look at percentages or standard deviations, but it will only let you select two statistics. You could select percentiles, you know, if you want to. Oh, yeah, percent. You can select percentiles. You can look at, give me the 10 I don't know, on the 90th percentile in literacy. And then you could, see here, you could say, want the table with jurisdictions at the top, or as on the columns.
What do you mean by jurisdictions?
Jurisdictions are the countries, basically, what we call the countries here. And they call it jurisdictions because it could be a country, it could be Belgium, Flemish, which is not a country. It could be, you know, we're done here. Well, other options that you have here is you can preview your results. And you get a blank report. So here's how the report's going to look like. You know, it's going to have the countries on the left. It's going to have the average with the error, the 10th percentile for males, 90% for males, and for females also, same thing. We're done. And let's say for the education level, we want to look at percent of people by level. So we don't want the averages. We want to know percent of people at each one of the levels. Below level 1, level 2, 3, 4, 5. Okay? Done? And now if you notice, but right here, you have the countries that are going to be involved, and then statistics that you're computing. And then this could also give you a cross tabulation. So whenever you pick variables more than one, then it'll also try to give you the cross tabulations. So I'm gonna close this because it might be. A little better? Yeah. So you'll have anyway. So we're gonna do the means and the percentiles by boys and girls, or boys and girls by males, females, so adults, and then we'll do the percent by achievement level by highest qualification.